Hello, this is Gary Sherman of Whaddadunce.com. Today we're going to continue on with our series on how the financial markets price risk. And this is part two, pricing investments via utility functions. And we went over utility functions in part one. In our investment options table, we have our four investments. RF is the risk-free investment. That's where the payoff is the same whether the market goes up or goes down. The payoff there is $1 million. And then we have investment A, which we have a little bit of dispersion. The payoff is 1.1 million if the market goes up, 900,000 if it goes down. Then we have investment option B, where the payoffs are either 1.2 million or 800,000, and then investment option C, where the payoffs are 1.3 million or 700,000. And then in that last column, we have the expected utility. And if you look at the bar graph below, those are the expected utilities graphed out. So for our risk-free investment, we have an expected utility of 5. For our investment option A, our expected utility is 4.9899, which is a little less. And then we have our utility from our option B, which is 4.9592, which is less than our risk-free investment and investment option A. And then we have our utility for investment option C, which is 4.9057. And here the utility is less than both our risk-free investment, our investment option A, and investment option B. So if the price of the investment was, say, $1 million, so in other words, we invest $1 million, and this is an immediate investment where we invest $1 million, and then the market goes up or down with a probability of 0.5, then we get an immediate payout. In this case, we would pick the risk-free investment because this has the highest utility. So what we basically want to do, if we were selling these investments, we know that we couldn't sell that investment in A, B, or C for $1 million. It would have to be something less. And that's what we're going to address in these series of slides. And then we have our utility equation there to the right. W subscript 0, that's our pre-investment wealth. We know what our wealth is before we put our money down on this investment. And then W is a post-investment wealth, and this is unknown. And remember, it could be either higher than $1 million or lower than $1 million, and time will tell. So our utility equation from part one is utility of our wealth is 5 plus 2 times the log of the ratio of our post-investment wealth, which is unknown, divided by our pre-investment wealth, which is known. So that's our utility equation, and that utility equation is reflected in the table above. So what we're going to do now is we're going to select investment option C, and we're going to go through the calculations, basically how we got the table in the previous slide for investment option C. So W subscript 0 in that table is our initial investment, which is $1 million. Now, if the market goes up, we get W subscript U, which is $1.3 million. And if market goes down, we get W subscript D, which is 700,000. So the probability that the market goes up is 0.5. The probability of the market going down is 0.5. So equation E1, this is our utility function, and we basically spelled that out in the previous graph, but just as a refresher, utility of wealth equals A plus B times the log of our ending wealth over our beginning wealth. So we said that A was 5 and B was 2. So this is our utility function. Then in equation E2, this is given that the market goes up. So in other words, we want to know what the utility of this windfall is. So we started out with $1 million, we invested it, and then we got a payoff of 1.3 million. So what's the utility of that 1.3 million given our utility function in equation E1? So if you go through the math, the utility of $1.3 million is 5 plus 2 times the log of our ending wealth of 1.3 million over our beginning wealth of 1 million. So our utility is 5.5247. So that's the utility of the market up payoff. But then we have the market down payoff. That's equation E3. So the utility of 700,000, which is what we get if the market goes down, is that same equation, 5 plus 2 times the log of our ending wealth now is no longer 1.3 million, it's 700,000. So it's a log of 700,000 over a beginning wealth of a million. So in this case, if the market goes down, obviously the utility is going to be less than if the market goes up. So our utility is 4.2867. And that's the utility of the market down payoff. So what we want to do is we want to take an expected utility. Because from an investor's standpoint, this is he wants to know at the end of the day, if this investment was run, 1,000 times, 10,000 times, 100,000 times, how many, what percent of the times would it go up, and what percent of the times would it go down? So in other words, in what percent of the time would I receive 1.3 million, and what percent of the time would I receive only 700,000? So we want to get an expectation here. So E4 is that expectation. So you can see that whenever we have that big E in the brackets, we want an expected utility. So we want expected, and then within the brackets is U of W, which is our utility function. So all we do is we take the results from E2 and E3 and just probability weight them. So what we get is the expected utility is going to be that 5.5247 from that's the utility of a market up times the probability of market up, which is 0.5. Then we want to add the utility of market down, which is 4.2867, times the probability of the market going down, which is 0.5. So at the end of the day, our expected utility is 4.9057. And if you go back to the previous slide, you'll see that in the expected utility column as far as our, so on average, this is the utility that we would expect from this investment. So now we're going to talk about the game show Deal or No Deal. I love Deal or No Deal because, as far as teaching economics, because it has a lot of economic implications. And in this case, what we're going to do is we're going to talk about Deal or No Deal and the certainty equivalent. Now, here's the game. There are 24 cases that contain an unknown amount of cash. The amount of cash in each case ranges from $1 to $1 million. But rather than just pick one case from the 24, the contestant can eliminate up to 23 cases from the board, leaving that one case on the board that the contestant can take home. And remember that the contestant can take home $1, he can take home $1 million, or something in between. Now, the host is Howie Mandel, but we also have a banker. And at multiple points in the game, a banker offers the contestant a various amount of cash to stop the game and keep that amount of cash and go home. So what the banker basically does is if let's say there's two cases on the board. One is 500,000 and one is $1 million. So the investor or the contestant in this case can basically say, well, the minimum amount that I can take home would be 500,000. And then the maximum amount would be $1 million. So the banker would offer something in between those two amounts. So every time that the game stops, the banker offers an amount of cash to the contestant to stop the game rather than take his chances on picking the right case. So this is a contestant's dilemma. Should the contestant take the banker's offer, receive a certain amount of cash now, or continue the game, where he receives an uncertain amount of cash at the end of the game? So here's the definition of a certainty equivalent, and then we'll apply it to Deal or No Deal. A certainty equivalent is a guaranteed amount of money that a person or investor could accept today rather than taking a chance on a higher but uncertain future payoff tomorrow. So here's the point. If the contestant takes the banker's offer and stops the game, the amount of cash offered by the banker and accepted by the contestant is the certainty equivalent. So in other words, the certainty equivalent is from the investor's, or in this case, the contestant's point of view, the banker would have to offer him this amount of money in order for him to say, you know what, I would rather take a certain amount of money that the banker offers me rather than taking a chance that even though I can make more, I can also receive a lot less. So now what we're going to do is we're going to apply the Deal or No Deal type of game show to our investment option C. So here's the revised game. A risk-averse investor receives one of two uncertain payoffs. If the market goes up, he receives at 1.3 million. If the market goes down, he receives 700,000. So the uncertainty equivalent is the amount of cash that the investor would take now, so as to end the game. So if we were doing a deal or no deal, there would basically be two cases on the board, one with 1.3 million in it and one with 700,000 in it, but we don't know which is which. So what we want to do is we want to go through equation E1. What we want to do is we want to calculate that certainty equivalent. What we want to do is we want to take the utilities of receiving a certain amount to equal the utility of investment C, where I roll the dice. So E1 is that equation. So we say that the utility of our certainty equivalent equals the expected utility. So using that equation, what we want to do is we want to go to E2. All we're doing is just restating equation E1. Rather than have our utility of our certainty equivalent, we're actually going to take our utility model and spell that out. So the left-hand side of E2 is our utility equation, and then we're going to set it to our expected utility. And then E3, that just solves for the certainty equivalent. So if we plug in the utility model parameters from the previous slide, the certainty equivalent is E4. So what we're saying is our certainty equivalent is W subscript 0, which is our initial wealth, which is a million, times the exponential of our expected utility from that investment, which is 4.9057, minus A over B. So if we go through the math there, our certainty equivalent is $953,939. So what this says is that the investor would be indifferent between taking a chance on $1.3 million versus 700,000 or receiving 953,939. Both are equivalent. So up until now, we assumed that all our investment options, whether it's a risk-free investment, option A, option B, or option C, we assumed that that was immediate investment. So in other words, we would invest X amount of dollars and immediately receive either a market up payoff or a market down payoff. But what we're going to do right now is we're going to say that rather than having an immediate investment, we're going to add some kind of term to it. So in this case, we're going to assume that we can invest at the beginning of year one, and then at the end of year one, that is when we receive the investment payoff, up or down. So if you look at that table, our expected investment payoff at time t. So in other words, at the end of year one, we probability weight all of the payoffs. So we expect to receive $1 million. So the certainty equivalent of that $1 million is 953,931, which we calculated on the previous slide. But now we're going to assume that we have this annual interest rate of 4.7%. So if we looked at E1, the investment made at time zero. So in other words, we know that if we take the certainty equivalent, which is remember that we're indifferent between the certainty equivalent of 953, 939 and rolling the dice on our bet. So if we receive the 953, 939 at the end of 1 year, what would that be worth? So we take the certainty equivalent and we divide it by 1 plus R, which is 1 plus the interest rate of 4.7%. So E2 does that. It basically says is that investment at time zero, remember that we receive the payoff at the end of year one. The investment at time zero or at the beginning of year one is 953, 939, which is our certainty equivalent, divided by 1 plus our interest rate of 4.7%. So the price of that investment would be 911,117. So what this says is that I have this game where at the end of 1 year, I'm going to either receive $1.3 million or $700,000. But I can also have the option of receiving a certainty equivalent of 953, 939. And the question is what would I pay for that investment today? And an E2 basically says is I would pay 911,117 for that investment. So now what we want to do is we want to calculate our return. So what we do is that is done in equation E3. So our investment C annual return is our expected payoff, which is $1 million, divided by the cost of that investment. So our expected payoff is going to be at the end of year one, And then the cost of that investment is going to be 911,117. Subtract 1. So our annual return is going to be 9.76%. This can also be viewed as a discount rate. So in other words, an investor who would take this type of investment where there are two payoffs of basically with 30% dispersion, he expects a 9.76% return. So that's the kind of return he would demand in order to invest in this game. So in this slide, we're going to take a look at the investment options risk-adjusted returns. So that table pretty much says it all. So in other words, we have four investment options, the risk-free one, A, B, and C. And notice that we talked about risk in the previous slides, and we define risk quantitatively as dispersion. So for our risk-free option, there's 0% dispersion. Option A is 10%, option B 20, option C 30. So what we're going to do is we're going to take the mathematics that we went through for option C and apply it to all our investments, which basically are our investment options. So the investment price, this is what we would pay for those investments now. So if I had the risk-free option, I would pay $955,110 for it. If I opted to go with option A, I would spend something less, $953.22. If I said instead I'll go option B, then I'll even pay less than that, $935,813. And then an option C, which we calculated in the previous slide, of $911,117. So our investment returns are 4.7% for the risk-free, and that makes sense because the 4.7 is our interest rate. So therefore, the investment return on a risk-free investment would be that same 4.7%. Option A would be 5.23%, option B 6.86%, and option C 9.76%. And those percentages are graphed in that bar chart below. So we can also look at these as a discount rate. So if I had a risk-free investment or something that was risk-free, I'm going to receive cash at the end of a year guaranteed, then I would discount that at 4.7%. If I had like an option A, or I could receive 1.1 million or something less 900,000 with that's 10% dispersion, I would basically demand something more of 523, and then we go option B and option C. And so these are our discount rates for those various investment options given the dispersion. So come join our community at Whaddadunce.com. It should be fun.